Okay. Well, welcome everybody. I'll introduce our special guest star later on, just before he speaks. Let me apologize for the way the previous class ended. There was some sort of power catastrophe that kicked me off, and by the time I had rebooted, Zoom was not comfortable with me restarting the meeting. So it's good that that was at the end of the class, even though, at the end of our time, though I would have gone on for another 5 minutes if not so rudely interrupted. Well, this is our second session on logic. And I have a few things that I want to say before I turn things over to Dan to talk about the real logic. And these are what you'll find on the handout. So let me just put that so we can all look at it. Okay, so I mentioned this parallel last time between two ways of construing a distinction between implicit and explicit. And the one is within reason relations, where if gamma implies A, we say all the members of the premise set gamma are its explicit content. That's what it explicitly contains. But because it implies A is part of its implicit content. It implicitly contains A in the literal sense that it's implied by A. And there's a parallel to this in our deontically two-sorted bilateralist normative pragmatics, where we understand what it means to say that gamma implies A, as saying that explicit acceptance of all of gamma precludes entitlement to deny A. That's how we're understanding an implication relation, and there's a corresponding treatment of incompatibility. But also I said, it seemed to me that was a good thing to mean by being implicitly committed to accept A. After all, you're not entitled to reject it. Now, that's not the same as actually accepting it, as explicitly accepting it. It's only an implicit, it's only something that's implied, but that's the only option that's left open to you. You might take no stance at all. That's why there's a difference between explicitly accepting it and only implicitly being committed to accept it. But these two senses are entirely parallel. And because of that, if we move to look at explicitation on the side of reason relations, when we make the implicit content A explicit by taking it as, accepting it as a premise, and then look at how that changes what's implied. And remember here, the structural principle, cautious monotonicity, CM, says that explicitation doesn't lose any consequences, and cumulative transitivity, CT, says that explicitation doesn't add any consequences. So together they say that this rational process of explicitly accepting as a premise something that's implied by the premises you already accept is inconsequential. It makes no difference to what's implied, to the implicit content of that the implicit content of the new explicitated premise set is just the same as the implicit content of the old original premise set. And now I want to say that there's a parallel to explicitation on the normative pragmatic side as well. And I want to call it inferring and treat this as a definition of inferring. By inferring, I'm going to mean explicitly accepting what you're implicitly committed to accept in the sense of the first parallel. That is, if an implication holds gamma implies A, you're precluded from entitlement to reject A. Implicitly, you're committed to accept A. If you embrace that, if you explicitly accept A, that's drawing a conclusion. That's rationally following out the implication and explicitly accepting what you're implicitly committed to accept. That is what's implied by what you do explicitly accept. I think that's a good thing to mean by inferring, is that act of explicitly accepting, overtly, actually accepting what you were implicitly committed to accept in the earlier sense. That's a paradigmatically rational activity, drawing conclusions, accepting the consequences that are implied by the premises that you have explicitly accepted. And now we can make an argument. If explicitation is inconsequential, if explicitating implicit content never makes any difference to what's implied by a premise set, then inference is impotent. Actually drawing a conclusion, making an inference, doesn't make any difference to what you're implicitly committed to. If inferring is not impotent, then explicitly drawing a conclusion, making an inference, can add new content, can make new claimables available as a part of the implicit content of one's premise set, and it might subtract some as well. And it seems to me obvious, one could argue for this, that inferring can in fact be ampliative, that realizing the consequences of what I'm already explicitly committed to can have real effects on what else I'm entitled to conclude. It can lead to new consequences, or it can be corrective. It can lead me to reject something that I was implicitly committed to accept before, once I realize that this is a consequence of my commitments. And if so, we have another argument against treating reason relations as having a closure structure. We can argue, look, inference is not in general impotent. So explicitation is not in general inconsequential. We argue by contraposition. And if that's right, then CM and CT are not part of the universal and invariable structure of reason relations. Now remember that they're not the strongest closure structures. The strongest form of monotonicity is MO. It says you can throw any additional premises into a good implication and it'll stay a good implication. And the strongest form of transitivity is mixed-cut that lets you combine the contexts of your implications. CM and CT are only sort of second-grade closure principles, closure being the combination of monotonicity and transitivity. And so to deny those is not just to treat reason relations as non-monotonic, but hyper non-monotonic. You're denying this even weaker form of monotonicity, cautious monotonicity, and denying even also the weaker form of transitivity. Not that those principles never hold, but that they don't universally hold. Now, remember last time I drew the consequence from this. If we give up the idea that reason relations in general have the structure that Tarski and Gensen identified as the structure of specifically logical reason relations, namely that they were fully monotonic and transitive, then we have to realize that the process of inference, of actually explicitating as a practical activity, is going to be path dependent, that there is no such thing as the set of consequences that I'm implicitly committed to by the claimables that I currently explicitly accept, that there's an order dependence. It depends on which of the consequences that I have now I explicitly embrace first. And among those, embracing all the consequences of the premise set is just one option among others, because once we don't have transitivity, it doesn't follow that if I do that again, I won't get to some new consequences. So I claimed in open reason, in the context of open reason relations, there's a phenomenon of rational hysteresis, of the path dependence of inference because of the path dependence of explicitation. And this, I said, was to see historicity built deep into the structure of rationality, that the order in which you actually extract consequences makes a difference to what further consequences there are. But our current concern is logic, and the immediate consequence is if, as I'm recommending, as the logical expressivist recommends, we think of the distinctive task of logic as being to codify reason relations, we should aim at a logic, our ideal logic should be able to codify open structured, substructural reason relations, not just closed ones. Indeed, the ideal logic should be able to express reason relations that are hyper non-monotonic and non-transitive, as well, of course, as the ones that are both. Let me stop there for a second for comments or questions. Yeah, Taylor. Oh, okay. Okay. So let me rehearse a little bit of what I said last time. So this time, just now, I introduced a technical definition of inference as explicitly accepting what one is implicitly committed to accept. Last time I introduced another technical definition of a vocabulary. A vocabulary, I said, is a lexicon, that is a set of sentences and a set of reason relations, which we can think of as just a set of sequence. And in spite of, in the light of the remarks I'd made about the dangers of demoting incompatibility relative to implication as a reason relation, because of notational convenience, we can actually encode the incompatibility and incoherence relations in the implication relations. And as long as we're vigilant about not letting that mislead us, that is, in fact, a very helpful thing to do. And for reasons that will become clear, it's useful to use the multi-succedent form of sequence, where we think of a sequence just as a pair of a set of premises and a set of conclusions. Remember, in Gensen, doing that with his basic set of rules yielded classical logic, whereas you could get intuitionism just by restricting yourself to a single conclusion. It turns out to be useful to use the multi-succedent form. Remember, Smiley and Rumfit developed their bilateralism so as to be able to get classical logic, but without having to go multi-succedent, because they said, I don't understand what it is to get to have a set of conclusions sort of understood disjunctively. But Restall and Ripley explained that to us. To say that gamma implies delta is to say that commitment, in our version, commitment to accept all of gamma precludes entitlement to reject all of delta. That's why the implicit commitments then look disjunctive. So we can think of that, the reason relations part of the vocabulary, just as a set of pairs of sets of sentences, premise sets and conclusion sets. In those terms, we can think about logic now. Logical vocabularies are rational metavocabularies. They're metavocabularies because of their relation to some base vocabulary, and they're rational metavocabularies because of their relation to the reason relations of those base vocabularies. I introduced a characterization of the distinctive expressive role that distinguishes specifically logical vocabularies, saying that logical vocabulary is elaborated from and explicative of the reason relations of the base vocabulary. Elaborated from and explicative of, LX for short. Logical vocabularies are distinguished among rational metavocabularies, that is, ones that characterize the reason relations of their base vocabularies, in that they're conservative extensions of their base vocabularies. Other rational metavocabularies, paradigmatically semantic metavocabularies, which also characterize the reason relations of their base vocabularies need not be conservative extensions of their base vocabularies. And by saying they're extensions, I mean the lexicon of the logically extended vocabulary includes the lexicon of the base vocabulary. It includes the sentence letters of the non-logical vocabulary we start with, and the reason relations of the logically extended metavocabulary include as a proper part all the reason relations of the original base vocabulary, whatever implications and incompatibilities there are relating the material base sentences carry over into the new vocabulary. Now, I'm going to say a little bit more about that, elaborated from part of the LX characterization. First, let me remind you of the two things I said about the explicative part as suggestive, but more than, I hope, merely suggestive elements, that conditionals as a fundamental kind of logical vocabulary are going to have and be defined by their distinctive expressive role of making explicit in the form of claimables, things you can express in declarative sentences, implications. And what we mean by that, we can see looking at this deduction detachment condition on conditionals, that some premise set gamma implies if A then B, A arrow B, just in case if you explicitated, if you added A as an explicit premise, B would be part of the implicit content. That is, that gamma together with A implies B. That's what you're saying when you say that gamma implies the conditional if A, then B. And in the same way, the distinctive expressive job that defines negation as a kind of logical vocabulary is that its job is to make incompatibilities or incoherence, two ways of talking about the same thing, to make incompatibilities explicit in the sense of introducing sentences that say the two things are incompatible. And here we can see as a suggestive, but more than suggestive, substantive condition on negations, the incoherence incompatibility, II condition on negation, that gamma implies not A just in case gamma is incompatible with A, which in the sequent calculus, in the multi-sequence sequent calculus, we're going to write by saying gamma comma A implies the empty set, an empty right side. So those two principles indicate what we can mean by saying that the logical vocabulary gives us the expressive power to make explicit the reason relations of the base vocabulary. Now, Dan's going to talk about that explication condition in much more detail, but I wanted to remind us of that. And I added two further conditions on an ideal logic, that logical rational vocabularies, anyway, the ideal ones, should be universally and comprehensively LX. To say that they're universally elaborated from an explicative of base vocabularies says it doesn't matter what base vocabulary you start with. You ought to be able to codify its implication and incompatibility relation using that logical vocabulary. And to say that the ideal logical vocabulary is comprehensively LX is to say that not only does introducing the logical vocabulary make it possible to make explicit the reason relations of the base vocabulary, but it also makes it possible to make explicit in that logically extended vocabulary the reason relations of that very extended logical vocabulary. That's the comprehensiveness condition. Now, as I say, this is what an ideal logic would be. In the logic group over the years, I spent a lot of time setting up criteria of adequacy for the ideal logic. What would you, if all of your dreams came true, what would logic do for you? Well, there's a lot of things. I mean, the ideal logic would complete the system of German idealism. I mean, maybe the ideal logic would make me nicely buttered toast every morning for breakfast. It's easy to say what, if your dreams came true, logic would do for you. Well, this is a somewhat more restricted set of demands than those, though parenthetically, you'd be surprised how close the logic Dan and Ulf came up with comes to completing the system of German idealism. But that's a story for a different occasion. Suffice it to say that I was completely incapable of coming up with a logic that would meet these ideal expressive conditions, but happily they weren't, and that's the one we're going to talk about. So the last thing I want to do before letting Dan tell us about explicitation and what NMMS, that ideal logic, will do for us, is rehearse explicitly what the conditions on the elaboration condition is. So to say that the logically extended vocabulary is elaborated from the base vocabulary, and furthermore is elaborated from it in a way that makes it a conservative extension of the base vocabulary. Well, that means that there's got to be a function that if you feed it some base vocabulary, because we want it to be universal, that's any vocabulary, any set of sentences, and any reason relations on them. It should generate a logically extended vocabulary that includes the base lexicon, but also logical compounds of it, and includes all the reason relations on the base vocabulary, but also extends that to reason relations involving logically complex sentences formed from it. And I think it's worth lingering a little bit on how that happens. So this is what I was talking about when digitally interrupted last time. If we just think about the extension of if we just think about how the extension of the lexicon works, that's really the model for how we're going to extend the reason relations. Obviously, all the action is happening on the elaboration of reason relations, relations of implication and incompatibility, governing the logically extended language, the one that has conditionals and negations and conjunctions and disjunctions anyway in it. That's where everything interesting is going to happen. But we can understand how that works by looking at how we extend the lexicon. So here in 6 is the thing I'm concerned with. We can define the new lexicon, the logically extended lexicon, as the smallest set. We have to say by inclusion, because this is now going to be an infinite set. That's a superset of the lexicon of the base vocabulary. That's the base of our induction. So we start with L0, the original lexicon, and we're going to now expand it by this rule, that if alpha and beta are anywhere in the extended lexicon, we start with all the elements in the base lexicon. If those are in L, then so is not alpha, and so is alpha arrow beta, and alpha conjoined with beta, and alpha disjoined with beta. And we're looking at the closure of the base lexicon under this rule, or this set of 4 rules, if you want to think of it, so that not only is the conjunction of any 2 elements of the base vocabulary in it, but the conjunction of anything you can get, anything that's in the extended lexicon is also in it. And that's why it ends up being an infinite set. There are infinitely many sentences in it. Each of them is only finitely long, only has a finite number of atoms in it, and only a finite number of connectives in it, but there's no limit to the length, to the finite length that you can have of it. So the way we get the new lexicon, we get all the logically complex sentences that you can form from the atoms by negating them, forming conditionals, conjunctions, and disjunctions from them. And here we do use a closure operation. This operation is monotonic, it's transitive, and we're talking about the closure here. I hope that's clear. As I say, this is usually done just in a sentence in your logic book, but we're going to do exactly the same thing to extend the reason relations. Here we say, well, all the basic all the implications and incompatibilities, well, just the implications since they codify the incompatibilities, all the sequence of the base vocabulary are included as good sequence in the new vocabulary. That's what in 7, the axiom of the system NMMS says. If that turnstile is marking sequence in the base vocabulary, any sequence that's good, that's in the base vocabulary, also is good in the extended vocabulary. That's like saying that L0, the lexicon, is in the extended lexicon. And then we close under connective rules. And this is like the inductive step of the definition. This is how we're going to get more than the sequence that we started with. And here, just as an example, look at conjunction, the conjunction rule. Here we say, if any sequent of the form that appears above the line is in the extended vocabulary, then the sequent of the form that's below the line is as well. And that's true for both of these rules, and that's going to add implications involving conjunctions on the left and on the right. And to get the logic, we just do that with a bunch of connective rules, each one of which tells us that if some sequent is in the vocabulary of the logically extended language, then so is some other sequent. And we're starting off with the sequence that are in the base vocabulary. So this is the set of definitions of non-monotonic multi-succedent logic. NMMS is what we call this expressively ideal language. It's got rules for the principal connectives, the conditional and negation. Those are the expressive ones. And also for the aggregative auxiliary connectives that combine premises and conclusions for the other rules, what I derisively referred to last time as Boolean helper monkeys. But we've got these four sets of connectives. And the point is, what they let us do is elaborate the sequence of the base vocabulary into a set of sequence that relate sentences in the logically extended language. Okay, so that's how the elaboration works. That's what specifying a logic is specifying how you elaborate the lexicon of a base vocabulary and how you elaborate the reason relations of the base vocabulary. So as to get a new vocabulary, that is a new lexicon of logically complex sentences formed from the atoms in the base, and a set of good sequence relating sets of sentences in that logically extended lexicon. Okay, is that clear in general as to what we're doing? Okay, that was all I wanted to say today. Let me introduce to you Dan Kaplan. Some of you know him. He's a proud Pitt product, defended his dissertation last December, though you will see he's been extremely active for years before that. If you noticed the Logica paper that I had us read last time is from 2017. He already had done this work on NMMS back then. And though he talks about it in his dissertation, there's a lot of other stuff going on in the dissertation. It's not just a logic dissertation. And because I think it's so interesting, that's why I didn't just give you on the website the logic chapter from it, but gave you the whole dissertation. So if you're interested in looking at the rest of it, it's if you're going to write a dissertation, you need to read some good ones, and this is a good one. Anyway, Dennis worked for many years in the logic group role, research on logical expressivism, and what he's going to present is this week, and then 2 weeks from now, he'll be presenting his implication space semantics. But what we're looking at now is NMMS, and in particular, how he made precise the demand for the expressive power of the logic, that it explicate the reason relations, that it explicitly codify the reason relations, how he made that explicit and then satisfied those criteria of adequacy in two different ways, in showing the expressive completeness of NMMS in a particular precise sense, and then showing how you could augment the expressive power of traditional propositional logic by introducing operators, behave like modal operators, that let us codify local regions where monotonicity and principles hold, where various structural principles hold, where they don't hold globally, but we say they do hold locally. So let me then turn things over to Dan.
Thank you. So I'm recovering from a cold, so sorry if my voice is off or if my energy is particularly low. I don't know that I would recommend reading my dissertation, but feel free to, I guess, if you want. Yeah, so I'm going to be talking about making logical expressivism the idea of precise, and this idea of expressive completeness, which I'll say more about once I make the idea precise. Let me share my screen. Actually,
And that worked.
Yes. Well, I also wanted to, I can share that file as well, if that's easier. Yeah, so this is just the file I'm looking at, but I figure if I share the screen, you can see what I'm looking at. Okay, so I think the first bit of it that I go through probably repeat some of what Bob said, but so maybe I'll be a little bit briefer, or I think I can be. So the idea behind logical expressivism, as I understand it, is that the role of logical vocabulary is to make explicit, or it's elaborated out of a pre-logical vocabulary, and it makes explicit what we might call the core semantic features of that vocabulary. So I think essentially what follows from what, and which things are incompatible with which things. And sort of the most basic case, the way it does that is through the conditional and negation. So we want to know which things follow from which. We have a conditional around that can tell us that, or at least we should place conditions on the conditional such that it does do that. And likewise for the negation with respect to incompatibility. I think Bob had in his handout the exact formulation of those. I think there's an additional thing we should want it to do, which is that as inferentialists, so what we count among the core semantic features are those, but I think in addition, since we take the consequence relations that give the sentences we're looking at content to be material, meaning substructural, we should also be interested in cases where structure does apply. So it is a feature of an implication that it is monotonic, an important feature or a semantically significant feature. So we should want to be able to make that explicit, and that should count as a bit of logical vocabulary because it makes explicit that feature of implication. And these two notions, I think, come apart a little bit. So expressing the core semantic features like or implication and incompatibility and expressing these further features, which are perhaps not, which only come into view if you want to give up the structural features of implication. So if you think that material consequence plays an important role in generating content. So I think it is possible to be, maybe I do think it's possible to be a logical expressivist without going in for this second sort of thing. If one thinks that consequence is fully structural. But that's not the view, I guess, that I'm representing, and I don't know how much of an argument I'll have. Or I mean, Bob advanced some arguments, I think, for thinking that's wrong, and I'll mention some things briefly. Okay, so with regard to the first one, what we want, or the role of logical vocabulary, is to make explicit in the object language those core semantic features of sentences, namely what follows from what. What we want is some way of making precise the idea that the introduction of new vocabulary allows us to say that certain implications hold or don't hold, or certain incompatibilities. Certain things are incompatible with other things. And the precise expression of this idea is on page 2 in this very long and complicated formula. But the core idea is something like the following. The introduction of logical vocabulary takes language in a consequence relation that contains no such vocabulary and maps it to a relation, or a language in a consequence relation that does contain that vocabulary. And the question is, what sort of constraints should we put on this relation, or what sort of features should we be looking at of this relation to call it explicative? And if it is, then we should think that it's an interesting relation for logical expressivists to care about, which is to say that the logic that characterizes that relation is one that logical expressivists should care about. And as I see it, what we should think is that each implication in the logically extended language should express exactly some set of implications in the pre-logical language. And the converse of that will also hold. So for any set of non-logical implications, there should be exactly one implication of a logically extended language that corresponds to it, that holds just in case it holds. Or we should say that expresses exactly that, exactly those features of the meaning of the sentences. So let me, maybe it be...
So, I mean, can I say, this is the key point. This is the key thing that Dan can show NMMS does, is that if you take any sequent in the logically extended language, so any set of logically complex sentences as a premise, and any set of logically complex sentences as a conclusion, any sequent that actually holds from this, you can trace that back and say exactly what set of sequence in the base vocabulary it is that are necessary and sufficient for this sequent to be good in the logically extended language, and vice versa. Pick any arbitrary collection of sequence in the base vocabulary, and he can derive exactly what single sequent in the logically complex language it is that will hold if and only if that collection, that arbitrary collection of sequence in the base vocabulary holds. So,
yeah, that's right. Maybe I shouldn't have front-loaded the punchline, but that is the punchline. But maybe it'd be helpful anyway if I walk through the formalism. I mean, I'm going to go through it in much more detail in a minute, but just to walk through what's on the second page there, so that, I don't know, it makes a bit more sense. So the idea is a logic is a function from base consequence relation to logically extended consequence relation, where these are just pairs of sets of sentences related by the symbol. And what we want is that for any arbitrary implication in the logically extended language, there exists some set of implications in the atomic language, so the second clause, such that whenever the atomic ones hold, so for any such pre-logical base atomic consequence relation, the logically extended one holds in exactly those cases. I should pause just in case. I don't know if that's clear or not. Hopefully, as I go through the proofs of some of this, it will become clear. Okay. The second thing, or the second notion of expression that we should be, or that I want to draw attention to, is the idea of a structural feature. So in particular, if we think that the content of sentences that we're interested in is material, meaning that the structural features of implication don't hold of it, so things like monotonicity and so on, then we might think that where they do hold is a semantically significant feature of those implications and of those sentences that stand in those implications. So a second notion of expression that we get as a result of that is the idea that we can express exactly where those structural features do hold.
If I can break in again here. So we talked about this a little when we talked about persistent implications. That is, even though we say, in general, it's not the case that if gamma implies A, then gamma together with any B, or gamma together with any delta implies A. Monotonicity doesn't hold in general. Still, for some particular implication, it may be that implication is good, no matter what else you throw in as premises. And so the idea is, well, those local regions of monotonicity within the sea of non-monotonic sequence, it would be nice to be able to express those, to have logical vocabulary that would let us tell, that would tell us of some implication, which it can codify, that was the first part, that it holds monotonically or for other structural features.
Yeah. Exactly that. Or, I mean, I guess, from my point of view, I guess the core idea here is that if you think that the content in sentences is material, then you're going to think that these structural, if you think it's material and you think it's articulated by the implications that those sentences stand in, then you'll think that those consequence relations are substructural. Nevertheless, it still seems significant when they do stand in those structural relations. So I do think there's such a thing as, when people talk about classical consequence, they're not talking about something, or there is a subject there, and we can think of, I think we can isolate the, so to speak, classical content of a sentence, or the persistent content of a sentence in the case of monotonicity. But I'll say more about that later. For now, I guess I'm trying to get the big idea on the table. So in order to make this precise, I think there are a few ideas we'll need. So the first is that we want to know not just where these structural features hold, but where they're preserved by the introduction of logical vocabulary. So it may be that there's some feature of the pre-logical atomic consequence relation that seems significant that is not preserved by the introduction of logical vocabulary. So the elaboration fails to preserve that feature. I guess there are two ways to go. One is to say, well, maybe that wasn't a significant feature after all. The other is to say, well, maybe that's another reason to be skeptical of that logic. In the end, what I conclude in the end is that I think if the logic is expressive in the first sense, then we should think if any feature that's not preserved is perhaps not interesting. Though I think that's maybe a controversial thing to say. But anyway, what we want is to say if a structural feature holds of a implication, then it also should hold of exactly those implications that that logically complex implication expresses, which is what I have in this inset equation also on page 2, where the SF in the Fraktur script just is shorthand for the structural feature holds of that implication. So if it's monotonicity, then it says if gamma implies theta is monotonic, so it can be weakened arbitrarily with additional sentences, then the atomic sequence that gamma implies theta express are also monotonic. They can also be weakened arbitrarily with additional sentences, though they would be atomic sentences because those are implications in the atomic consequence relation. Of those structural features which are preserved in this sense, we might want to know which we can express using logical vocabulary. So if we think that the ones that are preserved are significant features of the content of sentences, then as logical expressivists, maybe we should think there should be a way of making that fact explicit, so introducing that into the object language. I.e. additional bit of a logical vocabulary that expresses that implication is locally monotonic, for example, or transitive, or whatever it is, which is what this last inset equation on the page is expressing. So we need some way of marking the sequent, and then we want that marking to exactly correspond to the sequence that are that satisfy the structural feature. This is all kind of a bit abstract, but what it comes down to and what I'll show is that any structural feature that is preserved by, well, the particular logic I introduce, but what's significant about that logic is that it's expressively complete in the first sense. Any logic, any structural feature that's preserved can also be expressed. And I think this is a second kind of expressive completeness that we can put onto the table. Not only are all of the basic semantic features of content expressible, which is to say all of the implications and incompatibilities can be expressed by the logic, but also any structural feature which is preserved by such a logic can be expressed by an extension of that logic, which is what I show at the very end. Or that's maybe the big, either second punchline or bigger punchline. This will make more sense when I get there, but I hope that this is a rough outline of what is to come. Maybe I'll pause in case there's any, have I said anything particularly unclear, or if anyone wants to add anything, I don't know. Maybe not. All right. Maybe I'll can't remember what the rest of this. I think Bob went through these sorts of arguments already. But here I just wanted to reiterate that the consequence relations are material. We don't want we don't want to require that any of the ordinary structural features hold. And I think there are sort of ordinary reason considerations for thinking that there are many, for example, non-monotonic and non-transitive implications floating about. And then I think there are deeper inferentialist reasons for thinking that, namely, if the content of a sentence is articulated by the role it plays in implication, and this is articulated by the role a sentence plays as both a premise and as a conclusion, then we should think that we shouldn't want to require these things, which collapses a lot of these distinctions. Maybe I'll pause there in case because I don't know exactly, aside from what Bob rehearsed at the beginning, I'm not sure how much of that is just repeating, or if it's worth going through.
Well, I didn't have the wonderful past examples, but
I recently,
we've concentrated on the monotonicity and transitivity principles. I haven't talked much about containment, CO, or contraction.
Yeah.
Or reflexiveness.
I was thinking it wouldn't motivate relaxing contraction or reflexivity today.
I think that's probably wise.
But I will talk about CO in a minute. Okay, then let me go onward. The logic that we'll be using to the logic we'll be looking at that is expressively complete in the sense that I hinted to earlier is what we call NM-MS. So NM meaning non-monotonic, MS meaning multi-succedent. I think Bob had on his handout the rules of the system. But essentially we start with a atomic consequence relation, which is just a relation between sets of sentences. And then we have some way of extending it, namely via sequent calculus, which I'll talk about in a second. Importantly, we don't want to put any constraints on the atomic consequence relation. So we don't want to require that, well, actually, I'll take part of this back in a moment, but we don't want to require that it's reflexive, monotonic, contractive, or transitive. I should talk a little bit about containment. So containment says that that every sentence is reflexive, meaning it implies itself, and also that the implications where that occurs can be arbitrarily weakened. So P implies P, and also this remains true regardless of what additional premises and conclusions are thrown in. This structural feature is significant because it, as we'll see in a moment, this is what actually generates classical logic. It's a bit stronger than just reflexivity, which just says that every sentence implies itself, because it also has monotonicity built in to that. So it is a restricted monotonicity principle, but only in very specific cases.
It is equivalent, is it not, to Tarski's requirement when he formulates things in terms of consequence relations, that any premise set X is always contained in the consequence set of X. So all the explicit premises are also implied by that set. That seemed perfectly intuitive to him. Each premise implies itself. And then the idea was that happens no matter what else happens to be in the premise set. All the explicit content is also implicit content. That's the containment. The premises are contained in the consequences. And that turns out to be a more substantive and important principle than you would think.
Yeah, it's yeah, that's right. Yeah, which is I guess why we call it containment, because it looks like the Tarskian principle. Of course, we don't take that to exhaust the consequence relation, so there will be other things in it as well, and those other things won't satisfy the Tarskian closure principles. But this region of the atomic consequence relation where containment holds does satisfy them. Okay. The consequence relation is then defined via sequent calculus. So I'm not sure how much you talked about this sort of technical thing, but basically sequent calculus is contains rules for taking a representation of a implication and generating more of them. So we start with axioms. In this case, all the axioms are generated from this base consequence relation that we started with. So if something is a member of the base consequence relation, then it's also part of the logically extended consequence relation, or we have a proof of it. We can use it in our proof trees. And then we have the various rules for the logical connectives. I think, yeah, the conditional and negation are perhaps the more important ones. Or I mean, you can get by with just those two. But we can throw in the other ones as well. Yeah, I'll say more about this in a little while, I suppose. I wanted to say one other thing before we move too far further, which is a special case for imposing containment on the base consequence relation. Actually, I think we don't. I don't. My own view is that we shouldn't have to, but I do think that there are strong reasons for doing so. Not least of which is that traditionally containment has played a big role in formal logic in the past century. So being able to say that we have it too is a nice thing. But I think there's maybe more philosophically interesting reasons for doing so too, namely the following. So if we think that the content of a sentence is, or the content of sentences are individuated by the role those sentences play in implication, one thing we might want is that whenever two sentences are equivalent, meaning wherever one appears as a premise, the other could appear as a premise if substituted. And likewise as a conclusion. So wherever one appears as a conclusion, the other could appear as a conclusion. So this is the inset equation I have on page 6 towards the top. So wherever A appears as a premise, B could appear as a premise. Wherever A appears as a conclusion, B could appear as a conclusion. We might think that we want to be able to express a fact like this, meaning that we want these conditionals to appear as the conclusion of implications in the logically extended language. In order to have that happen, what we'll need is that they imply each other. So wherever they're intersubstitutable, we also want them to be, we also want them to imply one another. So this is what we have in the next inset equation. In arbitrary context, so with arbitrary premises and conclusions, A implies B and B implies A. I'm not saying you need to buy into this, but I think if you think that the content of sentences is individuated by the role those sentences play in implication, and you think this is the sort of fact that should be expressed or expressible in a logically extended language, then you might buy into something like this. As it turns out, buying into something like this is just equivalent to opposing CO on the base consequence relation. Or actually, it's equivalent to imposing CO on the logically extended consequence relation. But in a minute, I'll explain that if you impose it on the base consequence relation, you get it on the whole thing for free. So a short proof of this, which basically says, suppose A and B have the same meaning, meaning that they can be intersubstituted, then they imply each other in arbitrary contexts if and only if CO holds, and the proof is rather short. You get CO as a special case where the two sentences are equivalent. So A implies A is a special case of A implies B, where they're the same sentence. And you get the other direction. So CO holds by taking a particular instance of CO and then substituting B for A. So I think, yeah. So the upshot of that is that CO or containment has played a large role in the tradition of formal logic since Tarski. I mean, it's the Tarski enclosure principle, so it's nice that we're able to. It would be nice if we were able to say something about them, include them in some way, even if they have if they don't have a central role. That we still think that this is a feature that all sentences do have, even if it's not the central feature of those sentences. But more importantly, I think there's something philosophically significant about containment, especially if you're an inferentialist and a logical expressivist, which is that it is equivalent to thinking that sentences with the same meaning also imply each other.
And let me just emphasize or clarify that saying that CO holds of some vocabulary is saying that all the instances of sequence that have some premise set on the left and one of the premises on the right hold. There's lots, in general, there's going to be lots of sequence that are not instances of CO that hold in the base vocabulary, say. But to say that CO holds there is to say that all the instances of sequence where the conclusion is one of the premises or a subset of the premises, that all those do hold.
Yeah, that's right. Or if it helps to, yeah. I don't know if this helps to think about it. Or if it helps to think about it as a constraint we might place on the base consequence relation. So this is something that the relation can satisfy, and saying that CO holds is just to say that the relation has this property, namely that all of the instances of CO are contained within it. Okay. I don't know if I should pause in case there's anything is particularly unclear. I'll just continue onward. So that's the logic we'll be looking at NMMS with containment imposed on the base consequence relation for the reasons I just outlined. As I'll show in a moment, the logic has a number of interesting features. The biggest one of which, at least for now, will be that it's expressively complete in the sense I talked about at the very beginning, in which I'll go over again, meaning we can express in the logically extended language arbitrary sets of implications. Okay. In order to get to that result, we need to show a few things along the way. In particular, we want to show that, well, some of these are important for something later on, but in any event. I'm thinking if I want to introduce these now or later. Okay, so at the bottom of 7, you'll start there. So all the rules of the sequent calculus are reversible, which will be significant for proving the expressive completeness, because we want that we can sort of unwrap sequence to get back to the atomic sequence that they express. I don't know if were you going to add something, Bob? Or
Well, I was just going to say that historically, Genson's rules were not reversible, and I guess he probably thought they couldn't be. It was important to him that his rules, each rule had more logically complex sentences below the line than it had above the line. And that meant that since everything was only finitely long, that you knew if there was a proof, it was only finitely long. So you could, he designed this for meta-theoretic reasoning about what was provable and what wasn't. His Finnish student, Kettinen, in his dissertation showed that you could reformulate things so as to get reversible rules. And basically, NMMS just is Kettenen's rules, Kettenen's version of Genson's rules. I don't know, is that true up to our mixed additive and multiplicative?
yes, it's basically the Kettenen rules minus the quantifiers. Or it's sometimes also called, in case anyone's, I forget how I get the chat back. Or sometimes in textbooks it's called G3CP. Is that it? Or is it GCP3? It doesn't matter. It's the third Genson system of classical propositional logic, is what it means, which has this version of the rules.
Maybe it would be good to say something about CO and classicality at this point, since
I'm not sure how you mean. Or do you, relating to the choice of rules, you mean?
No, about what's special about NMMS reconstructing classical logic, so what you have to do. The fact I'm thinking of is that basically, if you apply the rules of NMMS to a base that only has instances of CO in it, so a really boring base, then you get classical logic. And our view is that's the thing to understand about classical logic. It's natural in that sense. That is, if you have a really boring, we sometimes call it flat, base vocabulary, where the only good implications are instances of CO. That is, where the conclusion is already one of the premises. If those are the only good reason relations in the base, then these rules give you classical logic. And as a result, if you restrict yourself to bases in which all the instances of CO hold, then the logic that you get is supraclassical. You were going on to say something about supraclassicality, I think, Dan.
Yeah. Um, that's right. In the advantage of the Katonen style rules over the Gensen style rules, and I don't have the Gensen style rules on the handout, so maybe this comment will be opaque. But the advantage is precisely that they're reversible. And the reason this is an advantage is that in Gensen's system, one thing he proves is that you don't need the cut rule. So you can, anytime you would stitch two proofs together, you could just construct the proof outright. In Katonen's system, you also get that you can also push all the other structural rules to the top of the proof tree. So contraction and monotonicity, where this isn't necessarily true this isn't true in the Gensen system, that you can push those rules to the top of the proof trees because of how the rules combine.
Well, and we know of no reversible single succedent set of rules. And that's why we don't know how to build an expressively complete single succedent system. That is, we can do it for logics that are sort of classical, that have classical logic as a degenerate special case. That's what an MS is. It's got all sorts of more interesting things than classicality. But if you suitably restrict the base to these boring flat ones, you get classical logic. And if you have at least all the CO sequence, as well as some other interesting ones, then you'll get all the theorems of classical logic will hold in your system. But the corresponding intuitionist system, where it's single succedent, because you can't do the Kettinen trick of getting reversible rules, you also can't get the kind of expressive completeness, certainly the first kind of expressive completeness that Dan was talking about. His proof essentially depends on being able to go back and forth between what's true in the base sequence and what's true in the sequence involving the logically complex sentences in a way that this reversibility is essential for. So this is a remarkable special case. And again, this is probably something that's special about classical logic, or supraclassicality at any rate, that comes out in this only being possible in the multi-succedent setting, which is what gives us classical logic. Anyway, gave Gensen classical logic.
Yeah, that's right. So the reversibility means you don't get any convergence of proof trees. So it's not the case that you could start with two different sets of atomic sequence and end up at the same thing, or you don't get any branching when you're going in the opposite direction of the proof tree, i.e. points where it's there are several possibilities for how you could decompose it further, or several valid possibilities for how you could decompose it. So it's the fact that it's multi-succedent and the fact that it's the Kettinen rules that allows for the precise notion of explication, and so the precise notion of expression that I'll be drawing on.
Okay, Dan, looking at the time, maybe now's a good time for us to take 15 minutes. So we'll come back at 2:40. Yes. So Dan's going to talk about the two dimensions of expressivity that he mentioned before, the capacity to express arbitrary combinations of sequence in the base vocabulary in the logically extended vocabulary, and to understand arbitrary sequence in the logically extended vocabulary in terms of exactly what they say about the base vocabulary on the one hand, and the second kind of expressivity, being able to mark explicitly in the logically extended language, now using some additional connectives besides the traditional ones, local islands where structure holds in the base vocabulary that gets preserved in the logical extension, so as to say explicitly where we've got persistent implications, so monotonicity holds, and so on. Yes, Dan.
Okay. I can share my screen again. Great. Okay. Yes. Before I do that, maybe I'll just run through very quickly some other features of the sequent calculus, just so that I have them on the table, because they'll be important for explaining these two notions of expressiveness. So one of the things here are some things that are distinctive of the Katonen rules. Some other versions of classical logic in a multi-succinate sequent calculus also have some of these features, but I think it's only the Katonen rules that have all of the ones that I'm about to list. So first, on page 7, it's enough that you can weaken a sequent with atomic sentences to be able to weaken it with arbitrarily logically complex sentences. If you can contract all the atomic sentences, then you can contract all the logically complex sentences. So contraction is also preserved by the rules. Containment is extended by the rules. So if containment holds in the base consequence relation, then it will also hold in the logically extended language. And this is what gets us the superclassicality of an MMS. So if the base consequence relation satisfies containment, then the extended consequence relation will satisfy containment. And as it turns out, that's just sufficient to get you superclassicality, because in the context of those sequences that satisfy containment, they behave basically the same as any of the formulations of classical logic. So in particular, I use Kenson's LK, because we can show that the rules behave the same, and also that we get all the same starting sequence. Okay. And then I mentioned before the break that all the rules are reversible, which I think is the most distinctive feature, and was what allows you to get many of the other ones I just listed as well. Okay. With all those on the table, let me talk about the representation theorem and the expressive completeness. There are actually two representation theorems that I go through here, but I'll focus on the second one, which is the one that's more important, I think. Second one on page 9 says that we can, if you take some arbitrary, let me back up one second. No, sorry. Yeah, the representation theorem says if you have a consequence relation that satisfies some modest set of constraints, then we can represent exactly that consequence relation in the logically extended language. And what those constraints amount to are similar to the rules that we've imposed. The first representation theorem, maybe I should back up and say what that one does. The first one just says that if you have a consequence relation, you can represent it. There is a way to get it from the base. So just take any arbitrary set of sequence, logically complex or not. There is a method of getting exactly that set of there's a method of getting at least that set of sequence in the logically extended consequence relation. So we can represent whatever consequence relation you want. There might be some other stuff around, but that's fine, depending on how the consequence relation was generated. The second one just says if there are some modest constraints on the consequence relation that you specify, it has to be closed in various ways, then we can represent it exactly. And what these two results give us, and the background material that's needed to get those two results, is this idea of expressive completeness. So in particular, every sequent in the logically extended language expresses exactly one set of atomic sequence in the base consequence relation, and every set of atomic sequence has one sequent that expresses it. Or we can find a sequent that expresses exactly that. It may be that there's several sequences that are equivalent in this way, but that's not an issue for the thesis. So this is what the inset equation on the first inset equation on page 9 says exactly this. The NMS is expressive, meaning that every sequent expresses some set of atomic sequence, and every set of atomic sequence finds an expression in the logically extended language.
And let me just interrupt with admiration about this. In the history of modern logic, no one has thought about a result like this. No one has thought about logical vocabulary as potentially having this maximal expressive power, that if you get the definitions right, you can capture exactly what the reason relations are in a base vocabulary. Classical logic is sort of in the vicinity. The Kettmann rules are a variant of Genson's rules for classical logic. And if you just apply them to flat, boring bases, you just get classical logic. But tweak them in the way that Dan has done in MMS, and you get this incredible demonstration of expressive power. So this is a real vindication of the program of logical expressivism.
And I think the reason I think this question has not really been asked is related to the second notion of expressivity, or namely that prior to, well, I shouldn't say that. I think traditionally the idea that logic has anything to do with material contents has not been on the table. And since it's not been on the table, the idea that there could be anything interesting to mean by expressing the pre-logical contents has also not been on the table, because the content of every sentence has been identical, except insofar as some of them have to be treated as different. But at least on the Tarskian conception, all the sentence, it's not an interesting question what the consequences of a sentence are, because they're the same for every sentence. Namely, if the sentence is atomic only itself, if it's logically complex, then it's just a matter of decomposing it.
So this comes out in the background assumption in logic that any two non-logical sentences can be intersubstituted without making any difference anywhere. And as long as they're not repeated, that's true of all the logically complex, within the logically complex sentences too. You can re-letter, change one sentence for another, and it makes no difference at all. And that's certainly not true in the application that we're talking about. A may imply B in the base, and that doesn't mean that, that means that you cannot necessarily substitute the one for the other. It's an interesting fact where you can, but you can't just substitute C and D for A and B if C and D don't imply one another. So traditional logic has been based on the idea of ignoring any difference in the reason relations that logical atoms stand in.
Yeah, I think if I wanted to dwell on that longer. I mean, I suppose well, let me say one thing, I guess. The difference is whether, I mean, I'm not sure how much you talked about this maybe earlier in the seminar, but I mean, I suppose the difference is whether you think you have to start with a material notion of meaning, and from that elaborate what a logic would be that governs those contents, or whether you start with a logic and from that find a way of getting some particularity and so that you can have individual meanings. And at least here we want the material stuff to come first. I mean, on pragmatic first understanding of meaning, you're going to want the material stuff to come first, I think. Okay. Yeah. The second notion of expressivity and expressive completeness comes from relaxing. So when the structural features of implication are relaxed, they may nevertheless still hold in some cases. So just because every implication is not monotonic doesn't mean that no implications are monotonic. So in particular, all the classical ones will be monotonic. We might think that there are some domains of reasoning where monotonicity still holds. So maybe mathematics and things like that. I also think that I don't have it in these sets of notes. And this is, I mean, the debate in the philosophy of language, but for example, the literal meaning of a sentence, I think, is only participates in monotonic implications. So adding in a I was going to say in a literal way. Adding the word literally to a sentence seems to make the sentence, seems to make implications in which the sentence participates monotonic, as long as literally isn't being used hyperbolically. Anyway, whether or not you agree with that is not so important to what will follow. Just that there are cases where implications do behave monotonically, and we might want to be able to capture those, because it does seem like there are domains where that's important, and we want to be able to make explicit when we're using sentences in that way. So in those domains, there might be further ways of restricting it, but at least so far as we're dealing with logic, which is to say something which is not domain specific, we're concerned with marking these features in general. So not marking when we're talking about physics, but marking when we're talking about this feature of implication, which may, as it turns out to be, also be particular to physics or mathematics or what have you. The result we get here is that if a structural feature is preserved by the rules, and we have a way of and we introduce a connective to mark it. So like the ones on page 10, where here we just introduce a new axiom, and then we introduce a modal box, which marks sentences that obey a structural rule. Then we can mark exactly where those structural rules hold, which is this expressive completeness result, also on page 10. So it's pretty straightforward. Yeah, so what this says is that if a sequence satisfies some structural rule, then we can introduce a connective to mark exactly that, so long as the structural rule is preserved by the rules of NMMS. So I call this expressive completeness because every structural rule or every structural feature that's preserved by the rules can be explicated, or we can introduce vocabulary to make it explicit that that structural feature holds where it holds. So this is a kind of expressive completeness result. Let me say a few more things, maybe, and then maybe I'll pause. So there are a bunch of structural features that we can do this for, and I show how to do that on 11 and following. So monotonicity, we can introduce a box that does that by marking the places where atomic sequence are monotonic. We can do the same with contraction, which I haven't talked too much about. But again, we can mark the sequence that will obey contraction. And then possibly of interest, we can mark the sequence that are classical by marking those sequence in the atomic consequence relation where containment holds, or the instances of containment in the atomic consequence relation. And if we mark those, we mark exactly, so from the first expressive completeness result, we mark exactly the sequence that are classical, and then we can introduce an operator to make explicit that fact, namely that those sequences are classical. And what we should understand that a bit of vocabulary to be doing is to be saying this is a classical consequence of whatever it is, or this premise understood classically, or I'm not sure if we have a locution in the premissory role so much, but you know, just take this sentence as sort of a bare token or something like that. Yeah.
If I could make one comment about this, particularly the monotonicity box. So the way I described this when I was talking about the persistence of implications was that mostly what we care about is the range of subjunctive robustness of an implication. That is, what additional premises can you throw in without infirming this implication, and which ones would be defeaters of it. For persistent implications, there aren't any defeaters. It has a maximal range of subjunctive robustness. That's naturally thought of as a necessity operator. This sentence holds, or this implication holds, no matter what. This premise set implies box A, that A holds necessarily. That is, no matter what else you throw into the premise set, you're still going to get A from it. That's a way to understand alethic modality, to understand alethic necessity, not thinking about possible worlds, just thinking about this structural feature of reason relations, of implications. I mean, incompatibilities can be persistent also. So this is an alternative to a metaphysically heavy sort of way of understanding that, which we'll talk about a little when we talk about semantics. But what Dan's monotonicity box does is mark the local regions of persistence. So it's much more flexible than just a necessity operator, never mind more flexible than reasoning in classical logic that only pays attention to maximally persistent implications.
Yes, go ahead.
Yeah, so my question's about the relationship of, so we're introducing these operators sort of to to account for local regions where certain structural conditions are satisfied. I'm wondering what the relationship these operators bear to, the case where we're sort of substructural cases where none of the constraints are satisfied. So in that case, so we said, for example, that the snake turnstile means commitment. What was it? Sorry, commitment to this premise set precludes entitlement to reject this other statement. So now, when you add this little m above it, so now it's like monotonic. Does the meaning of this change is that precludes entitlement to reject A, come what may? Is that the idea? Is it a different operator? What relationship does it bear to when it comes to commitment and entitlement? What change happens at that level? I don't. This is just for either you or for Professor Brandon.
I mean, I would say that's exactly what it means. That it means come what may. That is whatever else you add into the premise set. And the interesting thing here is, by contrast to classical reasoning, we're not assuming that that's true of all of the sequence. So we're just going to mark the ones where that is true. And we see the classical logician as restricting herself to the case where we've got that M, we've got that upward arrow, that persistence marker on the turnstile, and we'll mark those with necessity boxes. And then it's going to look from that point of view, from our point of view, as though the classical logician is restricting herself just to looking at sentences that start with a necessity box and ignoring all the unnecessitated ones, all the merely contingent things that might or might not be true, well, might or might not follow from some premise set in our setting. So yeah, the two things: to mark some of the turnstiles, that's the local island of structure, and then Dan's technique shows us how to fit any sufficiently well-behaved such restricted turnstile and explicitly express it in the language by introducing an operator that codifies it.
Okay. Sounds good. Thank you.
I think that's right. And maybe I want to add one other thing, because it was, I think at some point I was just thinking that these extra turnstiles floating about are just a technical convenience. It's just something we use to mark sequence in order to make the machinery come up with the right result, which is that you can put the box on some of these sequence if you want. But it's not really philosophically significant or something like that. But I think actually, it ought to be. And it ought to be something like what you were suggesting, which is that commitment to these precludes, commitment to assert these precludes entitlement to reject these, come what may. And I guess one thing I'm wondering in light of that, because one thing I've wondered is this idea of a structural feature is not very well delineated. Or I guess I'm very loose on what could count as a structural feature. But if these turnstiles are going to mean something like that, then it ought to be the case that the structural features that we pay attention to correspond to sort of significant features of the underlying practice. And it seems like come what may is a significant feature of an underlying practice. So it is the case that some implications can be treated as come what may. seems to be a significant feature of practice, whereas arbitrary ones that we can sort of cook up don't seem to pick out interesting features of an underlying practice.
Well, Dan, let me ask you about that. I mean,
yeah.
We could mark a turnstile with some special gamma and say that delta gamma turnstiles A, just in case, not only does delta turnstile A, but so does delta together with gamma. So this is a turnstile that just says, oh, and gamma is in the range of subjunctive robustness of this implication. And now, that might be, gamma might be in the base language, the sacred text. And we say, okay, this is not contrary to scripture. This implication goes through if, in addition to whatever premises you're actually using, we add the entirety of scripture to it, it still follows. And we might think, those implications are important to us. However, that privileged vocabulary has been picked out. Now, if that privileged vocabulary, if that gamma's in the base language, I take it that's going to be preserved by NMMS rules. And so that's something that your procedure would let us introduce a special operator to mark. Is that right?
Yeah.
And yet, and from your notes, I gather you're going to go on to say something about this. There are other things that seem like perfectly straightforward bits of structure that we can't do this with. For instance, cautious monotonicity, which, again, correct me if I'm wrong, but local regions where cautious monotonicity held in the base language, that doesn't get preserved by our rules. It only does if the entire base vocabulary meets a very strong, implausibly strong structural condition. It allows weakening under arbitrary subsets of consequences, I think. But at any rate, CM, the monotonicity condition that's just sort of next in line weaker than monotonicity, doesn't show up as interesting, as structural in the way that it's preserved here, or is it just, it's a nightmare for our logical machinery?
Yeah, that's right. It doesn't show. Well, CM just isn't preserved by the rules. CT can be with what you were calling a sort of extremely strong constraint on the base, or a plausibly strong constraint on the base. It can be. But the constraint looks different than CT, which is perhaps significant. So that constraint is preserved, but CT is not preserved. Yeah, I mean, there's a bunch of features that won't be preserved by the rules, and some of them do look significant.
So, I mean, this is just unexplored country, or anyway, undiscovered. We don't know how to express that stuff, some stuff, in the way that Dan has shown how to express a whole lot of structure, sort of including the one I just made up about, a distinguished sacred subset of sentences.
I'm not sure if anything enlightening to say. It would be interesting if there was something at least for some of these cases, philosophically interesting to say about why that practice is not significant, namely the CM1 or the CT1, or whatever it is.
I mean, here's a factoid in the vicinity. If you compare the arrow rules in NMMS to the DD condition, the deduction detachment condition, the double Ramsey condition on the conditional that I said for it to be expressive, you'll see, well, that's just what determines the right rule for the arrow. But it doesn't actually say anything about the function of conditionals on the left. Where do those rules come from? The L arrow rule in NMMS, well, it was a criterion of adequacy for these rules that they preserve CO. Dan's talked about the classicality, superclassicality, and so on. That means that from gamma together with A arrow B, that had better imply A arrow B. If not, the rules would produce violations of CO, even if the base didn't. And a relatively simple argument shows that the left rule for the arrow is just exactly what you need to get CO to hold when you extend the base with the two arrow rules. Basically, for gamma together with A arrow B to imply A arrow B, given the role on the right, that means that gamma together with A and A arrow B has to imply B, have to be able to detach on the left. And that's exactly what the left rule gives you. So we build into the rules as a constraint on acceptable rules that they preserve the stuff we'd like them to preserve, at least for the stuff we know how to do that for, which includes CO and it includes full monotonicity, but not this intermediate monotonicity principle, CM. What that means, I don't know. That is what the philosophical significance of the difference between the structural conditions that can be expressed in this way. Is it just we haven't thought of the right rules? The troubles with CM seem to go deeper than that. Okay, Dan, this was a detour from your discussion. I hope it was a useful one, but let me hand it back to you.
Yeah, I'm not sure. It was a useful one. I'm not sure what else to add to that. There are things that are different about CM and CT, I think, than the other structural rules. But I don't know what, if there's anything there like philosophically interesting to say. It'd be nice if there was. We need to think a lot more, I think. Okay. I'm not sure where it was. I think did I say everything I wanted to say? Let me just reiterate. Back on page 10, we have this other expressive completeness result. So for the structural features that are preserved by the rules, we can always introduce an operator to mark local regions of that structural feature. And in particular, show how to do it for monotonicity, contraction, and classicality. They're the regions that are classical. In the last bit of the notes I distributed, I show some cases of rules that in the first case are not expressive according to the first notion of expressiveness, as well as some structural features that aren't preserved by the rules and therefore can't be marked via modal operator. And in particular, so just reflexivity is not preserved by the rules. Containment is reflexivity with weakening, but if you just look at the instances of an atomic sentence applying itself, the rules of NN-MS don't preserve that feature, which is to say, which means that you can't mark it in the way that I outlined.
So
Yeah,
let me pick up on this local marking of the structure. We're doing something very radical when we say that in wanting a logic to be universally LX, so for any vocabulary, and we don't want to put any restrictions on the reason relation of that vocabulary. So it can be sort of arbitrary sets of pairs of sentences, pairs of sets of sentences, premise sets and conclusion sets. And if you say that to a proper logician, they'll say, well, what makes that a consequence relation? If it isn't monotonic, if it isn't transitive, those are the minimal structural conditions that make a relation between sets of sentences into a consequence relation. I don't know what you're talking about, the logician will say, but it isn't consequence relations once you drop all these structural requirements. What makes it a consequence relation other than that you keep saying it is? And it seems to me that that's a telling objection, but it seems to me that this second expressivity result of Dan's goes a long way to being a response to it, because it says, well, among the things we're calling consequences within this consequence relation, though we don't impose globally the conditions, the structural conditions that you say, as giving aid and comfort to the logicist enemy, the structural conditions that you say are necessary and sufficient for something to be a consequence relation. We don't impose those globally, but of course they often hold. You're right about that. Within these arbitrary things. And so what we're going to do is give you the expressive power to talk about those regions. Now, you say you only want to talk about those regions, that it isn't worth talking about the rest of them. Why? Well, you think that we'd completely lose formal traction on them. We couldn't say anything about them. Just anything goes. Anything can follow from anything. And we say, oh, no, that's not true. The first set of expressivity results shows that we can talk perfectly sensibly. Not everything follows from everything, but we can talk about what does follow there. And we can mark out the regions where monotonicity, transitivity, CO, the regions of classicality, we can mark out all of those regions. What you're saying is, well, you think those are the only interesting regions. Those are the only ones you want a logic to address. We say, well, we can do everything that you want to do as a special case if we were to restrict our attention to these special regions, these islands in a sea of structure, in a sea of open structure. So we can do everything you want to do. Surely that vindicates our willingness to talk about consequence relations that cover a lot more ground than what you're willing to acknowledge. Now, it's one thing to say, oh, wouldn't it be great to have a logic to do that? We had that idea long before Dan was able to show how to actually do it. But having that, it seems to me, softens the blow of this objection that we only think we're talking about reason relations. These are not reason relations at all. So Dan has here not only made precise the notion of explicitation, the sense in which the logic lets you say that reason relations hold, and furthermore that reason relations meeting these additional structural conditions hold. He's not only made that precise and shown that we can do that, but he's shown how to introduce these operators that codify, make explicit the regions of local monotonicity, where CO, where of containment holding, and so on.
You muted yourself, I think, the last thing you said.
I'm sorry. Please, back to you.
I think that's everything I want to say. So maybe I'll just summarize, and then if there's any questions, we can go to that. As you were saying, what we want is a logic that, I guess we want two things. First, we want to make more precise what it means for logical vocabulary to be expressive, or what exactly logical expressivism means, in particular the explicative of component of that, that logical vocabulary expresses something about an underlying non-logical or pre-logical vocabulary, and also a logic that sort of bears out that thought in an interesting way. And the precisification of that is that the two notions of expressive completeness that I put forward, so the first of which, that the logical vocabulary should allow you to express exactly what follows from what, in particular, which combinations of atomic implications hold, and also other significant structural features of implication, in particular the ones that we relax by understanding implication to be material, so monotonicity, transitivity, and so forth. That's what we want, and then obviously NMMS was shown to do all of those things, so that's a nice thing.
So if I could just append, so on this first expressivity, again, just to clarify this, suppose you take in the logically extended language just some arbitrary set of sentences. It's big. Maybe you've got 1,000 sentences. Some of them are 1,000 characters long with conditionals and negations and conjunctions and disjunctions. And we've just taken this vast theory formulated in the logically complex language. And now we take a bunch of consequences, similar language, all those sentences. Almost never will it be the case that the sequent that says, okay, from this premise set, from this theory, you can get these consequences. Almost never will that hold in virtue of logic alone, because we're just picking these arbitrary sets of sentences. All classical logic, which we've got a version of here, can do is tell you, oh no, that doesn't follow. that's not a classically valid sequent. But what expressivity in this first sense says is, well, we can tell you exactly what relations among the logical atoms are necessary and sufficient for this theory in the logically extended language to have these consequences. This is what needs to hold in the base. That's what, if you endorse this sequent in the logically complex language, that's what you're saying about the base. And any base that has those sequence holding in it, when you elaborate it according to the rules of NMMS, it'll turn out that this sequent is good. Not logically good, just good. We've got to distinguish between what the reason relations of the logically extended language is when we've elaborated it from some particular base or some set of bases on the one hand, and which sequence in the logically extended language hold just in virtue of the connective definitions. Those will be the ones that hold no matter what base you apply it to. They hold for all of those. So we need to sharply distinguish between the reason relations that hold in the logically extended vocabulary that's been extended from some particular base. We need to distinguish that from the ones that hold in virtue of logic alone. Those first, the sequence that hold in the logically extended language, those are going to be wildly non-monotonic and non-transitive. Well, if the base was non-monotonic and non-transitive, since those sequence are conserved, there's no new sequence involving only the base vocabulary that we get. If the implication relations in the logically extended language were monotonic and the base wasn't, then it wouldn't be conservative over it. So we've got a way of handling with the logical apparatus these massively non-monotonic, hyper non-monotonic, and non-transitive reason relations in the base language and in the logically extended language. If you just look at what holds in virtue of NMMS rules alone, no matter what the base is, that's a perfectly closed structural consequence relation. It's monotonic, it's transitive. That is, what NMMS is not really a non-monotonic logic. It's a logic for codifying non-monotonic and in general substructural or open structured consequence relations. And it turns out, who knew, that a perfectly monotonic and transitive logic, structurally classical logic, can codify and express these massively open structured, hyper non-monotonic and non-transitive consequence relations. So this project contrasts substantially with the way the subfield of non-monotonic logic is usually construed. That starts with a logic, typically classical logic, and adds non-monotonic inferences to it, to the logic. The logic endorses non-monotonic inferences. In our setting, thinking of the logical vocabulary as a particular kind of rational metavocabulary, one that extends a base vocabulary. It's the base vocabulary's structural principles that are going to determine what the structure of the reason relations of the logically extended vocabulary are. But the ones that hold in virtue of logic alone are plain vanilla as far as the structure is concerned. So once again, we want to say, well, the traditional logicians were not talking nonsense. It's just they were not exploiting the full expressive powers of the sort of logical machinery that they were introducing, which turned out to be incredibly sensitive to the exact formulation of classical logic. Genson's LK formulation of classical logic won't do it. His student Kettenen's will, if tweaked and applied suitably. But all of that is what Dan has shown here. So there's some of the details about how to show that in his notes here. Some of them you saw in his Logica paper that was on the reading list for last week. And there's a good deal more of this in the dissertation. Any last questions before we let Dan go for now? Okay. Well, thank you very much, Dan, for, first of all, for coming up with this wonderful logic, but in particular for talking about it today. And we'll see Dan again in 2 weeks to talk about semantics. Incidentally, a semantics for this logic, but by no means only for that. Okay, so next week we're reading Ulf's paper about the connection between bilateralist normative pragmatics and Kit Fine's truthmaker semantics. And Ulf will be here to present that material as well. So I will see you all next week. Hassan,